All right, welcome to 16.3, calculations of weak acids and bases. All right, so dilute, strong acids or bases. All right, so quick recap from yesterday. There is a big difference between a concentrated acid and a strong acid and a weak acid and a dilute acid, and for that matter, bases. Now we're looking at H's and A's. A for acid, H plus. We're going to increase the H plus. So we're looking at acids, but you can imagine the same holds true for bases. We would just have OH negative and probably a B before that, B OH negative. But these images here, we're looking at acids. Both of the first two pictures show concentrated acids. Both of the first two are concentrated acids. So they're concentrated because they both have a lot of the acid there. That's what a high concentration means. One of them, though, is a weak acid. So weak and concentrated are not the same thing, and weak and dilute are not the same thing. And similarly, strong and concentrated are not the same terms. We're talking about acids and bases. A strong acid means that it's going to ionize completely. We take a look at this one over here on the right. Notice how all the H pluses and A negatives have dissolved. There is no HA remaining in this picture here. That makes it a strong acid. The picture on the left, we've got a little dissociation. We've got one H plus and A negative, but most of this acid has remained together. That's a weak acid. Not much dissociation happening there. Most of those HAs stayed together. They didn't dissolve. They didn't ionize. They didn't break apart. So this is a concentrated because there's a lot of them there in a little area, a concentrated but weak acid. This is a concentrated strong acid, so concentrated because there's a lot there, strong because most of them, all of them actually, broke apart. That makes it a strong acid, so concentrated strong. Now we look at the two images on the right. Both of these are dilute, meaning there's not much acid per space. So both of them are dilute, but that has nothing to do with whether or not they're strong or weak acids. The picture on the right is a strong acid. It dissolved or ionized completely or dissociated completely. We have all H pluses and A negatives. The fact that they are completely dissolved makes this a strong acid. Now the pH may not be very low, even though it's a strong acid, because it's not very concentrated. It's a dilute strong acid. And we look here, here's a weak acid. Again, we know it's weak because it didn't dissociate very much. We only have one ionization or one dissociation. Most of those HAs are still hanging out together. So it's not a strong acid, it's a very weak acid. It did not dissociate much. And it's also dilute, because it doesn't have very many acid per square inch, or whatever unit of volume we're looking at, cubic inch. So strong, weak, concentrated, dilute. Make sure you're thinking about the terms that you use. They do have a good meaning. All right, so continuing to talk about that, strong acids and bases dissociate completely. However, this is going to take some thought process here. If the concentration of the acid or base is so dilute, it might not affect the pH. So let's take a look at an example. Let's say we have a concentration of 5.0 times 10 to the negative 11th molar HNO3. All right. So HNO3 is a strong acid. We're looking at the H plus concentration. Again, it's going to be like this picture here. It's very dilute, 10 to the negative 11th. but it is a strong acid, so we're going to have full ionization. Whatever concentration of HNO3 is, that will be our concentration of H+. Every single one of these guys will break apart, like in this picture here. It's a strong acid. So our concentration of H+ is 5.0 times 10 to the negative 11th molar. So we plug that into our pH equation, and we get a pH of 10.3. Ah, wonderful, you might say, and you might jot that down on the test and move on. Don't. Be smarter than your calculator. You need to think this through here. This is a pretty basic number. If I told you you have a base with a 10.3 pH in your hand, you should probably go wash your hands. That might burn a little bit. That's a pretty strong base you're looking at, 10.3 pH. So you're telling me that we put a strong acid into water and it made our solution basic? Well, that's not right. That's not possible. An acid cannot make a basic solution. So this is some thought process here. You have to think, hey, we've got an acid, ladies and gentlemen. It cannot give you a basic pH. So don't run with that. Be smarter than what your calculator says. The pH is 7. It didn't change. Putting that dilute of an acid, strong or weak, that dilute of an acid into water will not affect how many H pluses are in water. The pH will remain at 7. All right, weak acids and weak bases. So, weak acids and bases only partially ionize. It's actually, you can think of it a lot like the reversible reactions that we worked on 2 chapters ago. So in order to determine what the pH of a weak acid or base is, you have to consider the acid dissociation constant, which we call the Ka. Does K look familiar? The little a just stands for acid. Or a base dissociation constant. Dissociation, got some N's there, which is Kb, B for base. So remember our equilibrium constants. For example, nitrogen gas, hydrogen gas, making ammonia gas. The K equilibrium would be ammonia squared, because we've got 2 of them, over the reactants, nitrogen and hydrogen cubed, because there's 3 of them, and that's our K equilibrium. Well, Ka and Kb are the same thing. The K is an equilibrium for, you could call it a reversible reaction. There's a reversible reaction arrow again. So we have acetic acid here. That H can come off. Call this ethanoic acid, perhaps. But again, that's not a very, very strong conjugate base, I should say. It is a very strong conjugate base. So this conjugate base could grab that H plus back and move back in the opposite direction. It's a reversible reaction. So that gives us a dissociation constant that looks like this. We have our products on top, just like before, and our reactants on bottom, our concentration of reactant on bottom. So in order to solve for the pH, we need the H plus concentration. So if we're looking for the pH of a weak acid, we're trying to find the concentration of H plus. The concentration of one of the products? Well, this sounds a lot like ice table. Hooray! So, here we go. Here's the type of question we're looking for. Calculate the pH of 1 molar ethanoic acid. They gave us the Ka, 1.8 times 10 to the negative 5th. So I'm going to set up my dissociation constant. I had it on the last page. We're going to set that up. Ka is equal to products over reactants. And here's my ice table. Hey, look at that. Looks familiar, doesn't it? All right, well, initially, my concentration of CH3COOH was 1 molar. And I have 0 molar and 0 molar. Initially, I have no product to start. I'm going to change by losing X gaining x, and gaining x. So again, x can be the variable. We're not sure what that is just yet, but when we solve for it, hey, that's going to be our H plus concentration. So our CH3COOH, ethanoic acid, is going to go from 1 molar minus X. So that's what it's going to go down. We know our Ka, so we can plug that in. So we have X squared, 1 minus X. There's our 5% rule. We can eliminate that minus X if we so choose. We'll have to validate the 5% rule. Now we're finding the square of both sides. 1 on the bottom, we can get rid of that pretty easily. And we can solve for x, 4.2 times 10 to the negative third. And again, I'm going to keep this as 1 molar. If I'm using the 5% rule, I'm saying that the change of x is so small that we won't notice it. And indeed, I think that is the case. 1.00 minus 0.0042343. Would end up with 0.96, so you'd have a very small number, 1.00. It's probably going to end up being a fair assumption. Whereas our concentration of the ion acetate would be 4.243 times 10 to the negative third. And our concentration of hydrogen ions, there's the key. We're looking for our H plus concentration in order to solve for our pH. That's going to give us 4.243 times 10 to the negative third. And then finally, boom. Don't forget that just solving for X, or in this case, the concentration of H plus, is not your final answer. We're looking for the pH. So we need to take that concentration of H plus, and we need to solve for our pH. Don't forget to validate the 5% rule if you choose to use it. Our difference was 0.42%. Yes, definitely less than 5%. Valid assumption. Very cool. Got some homework to work on. You only get better with this stuff through practice, so take a look. 6 problems here for you. Not all of them are ice tables. I think there's only 2 or 3 ice tables on here. But take a look. Give it a shot. Good luck.
Daylight.